This is part 6 of lecture 8 of Elect 5300. In this lecture we'll be talking about a Bayesian estimation when both the mean and the variance are unknown. And in particular we'll be just paying most of our attention on what is the form of the conjugate prior, because we've seen that that's really the most important question. We'll start out by assuming that the mean is known, but the variance is unknown. So this situation, the hill location is always going to be at mu, but then the variance could change. Now, the precision is 1 over the variance, so in this case here, this one here actually corresponds to large precision, right? So we're very sure that the points from the distribution will lie close to the mean, then that's very precise distribution. Otherwise, this one is when lambda is small, when they're spread out more. So if we write the likelihood of the data given lambda the precision, that's just a Gaussian where we take the product for each individual data point. And what we've done here is we've just taken the standard deviation or variance, which is normally at the bottom, and moved it up to the top. So here we took the variance and moved it up to the top. Here we took the standard deviation and moved it up to the top when it becomes the precision. And what we can see here is that what we're interested in is really mainly the form of this likelihood in terms of lambda if we're interested in finding the conjugate prior. So we'll just focus on lambda here, and so we can forget about like this term here. We don't have to worry about this. So when we take the product over n pieces of data, the lambda here's are all the same, so I just get lambda to the n divided by 2, and the product of the exponential is just the exponential of the sum. So I just sum over all these individual data points inside there. And so if I look at this form here, then the conjugate prior has to be lambda taken to some power times e to the minus something times lambda. And so that's exactly the form of the gamma distribution, lambda taken to some power times e to the minus something times lambda. And so the rest of this stuff looks a little bit complicated, but it's important to just remember that this is not that important. This is just a normalizer to make sure that when I integrate this thing over lambda, the whole thing integrates to 1. So the form of this is a little bit complicated, but conceptually you don't really have to worry about this. So the expected value of lambda is just given by a divided by b, and the variance by a divided by b squared. And this is the form of different gamma distributions for different parameters a and b. This one here, when a is equal to 1 and b is equal to 1, is exactly the same as the exponential distribution. And this one here, when a and b is large, you can see it's kind of forming something that looks a little bit like a hill. In fact, it can be shown that the gamma distribution eventually approaches a Gaussian distribution when I get a lot, when a and b get relatively large. The key difference, though, between the gamma and the Gaussian distribution is the Gaussian distribution has probability from minus infinity all the way up to plus infinity, but the gamma distribution is only defined for positive values of lambda. Now that we know the form of the conjugate prior, we can find out what is the transformation that takes the parameters of the conjugate prior and turns them into the parameters of the posterior, which will have the same form. So we just take the prior distribution, which was the gamma distribution, multiply it by the likelihood, which was that Gaussian distribution, and we just combine terms here. So when we combine the lambda terms here, we get lambda to the a plus n divided by 2 minus 1, and the e to the sum of this plus this. So I combine those terms inside there. And so now I can see that this is exactly the same form as that. The only difference is that I've replaced the a 0 here by a0 plus n divided by 2. So in other words, when I have n pieces of data, I update the a parameter by adding n divided by 2. And I've taken b inside here and I've added a 1/2 times this sum here. So I get that. And I can take this, multiply and divide by n, this thing here is just the maximum likelihood estimate of the variance. So b is updated by n divided by 2 times the maximum likelihood estimate of the variance of all the observations. So then here you can see a0 is updated by half the number of observations, so a0 itself can be kind of interpreted as being half the number of effective prior observations, or 2a0 is equal to the effective number of prior observations. And if I divide this thing by n divided by 2, I get the variance of the data. And so by analogy, if I take b0 and divide by a0, I kind of get a measure of the effective variance of prior observations. Finally, I'd just like to discuss what is the conjugate prior when both mu and the precision are unknown. The likelihood has the same form as we've studied before. The only difference is now we're going to assume that not only lambda, but mu is also unknown. To find the form of the conjugate prior, I'm going to expand this quadratic out. So this term here will give me minus lambda divided by 2 times xk squared minus 2 mu xk plus mu squared. And I can factor out all the terms that don't depend on the data xk into one term here. So that's the lambda to the 1/2 e to the minus lambda divided by 2 times mu squared. And when I multiply it n times, it's just the same as raising it to the nth power. What I'm left with is just the exponential of minus lambda divided by 2 times the data squared, and minus lambda divided by 2 times 2 times mu times xk. And so when I take the product over the exponential, I get the exponential of the sum. So I get lambda, and then minus 1 over 2, and the minus 2 cancel here, so I get lambda mu times the sum over the xk minus lambda divided by 2 times the sum over the xk squared. And so remember, this is now has to be a distribution over lambda and mu. So everything else that's inside here I'm going to call a parameter. So here, for example, the n, I'm going to call it a parameter beta. This term here, the summation of the xk, I'm going to call that c. And this term inside here, I'm going to call that d. And it can be shown that we can further rearrange this thing here so that this is kind of the product of something that looks like a normal distribution in mu and a gamma distribution in lambda. And so we call this distribution the normal gamma or the Gaussian gamma because it's kind of a combination of those two. And intuitively this should make sense to you because remember when we were just trying to estimate the mean, we knew that the conjugate prior for the mean was a Gaussian. And when we were just trying to estimate the precision, we knew that the conjugate prior for that was a gamma. And so this is some kind of combination of those two. So in the final part of this lecture, we'll go on and talk about a family of distributions which is known as the exponential family of distributions, which captures a lot of the distributions we've talked about up till now.